Shucks. Okay. I would like to bring your attention up to the front, please. If you weren't here yesterday, there should be. Did I put the extras into the bin? I don't know if I actually did. Cassidy. Yes. Anybody else get a notes packet? Is anybody else not here yesterday? Did you get okay. I asked you to do one question, and people thought this question was so complicated, and I don't blame you for it. Okay? It's been a really long time since we've actually thought about this one little teeny tiny thing. It's been such a long time, and you've been doing stoichiometry for like 2 weeks now, 2.5 weeks. It's going to be tough to get your brain out of the stoichiometry mindset. Now, what I want to ask you, what is stoichiometry all about? Moles of one substance turning into moles of another substance, right? So we need 2 different compounds. In order to do stoichiometry, we need 2 different substances. Now, I totally agree with you. It absolutely looks like there's 2 different things on this slide, right? One of them says KHP, and one of them says KC7H4O2COOH. Okay, no problem. Wim, question, comment. It's saying that this thing is this thing. It's a shorthand. Yeah, KHP. It's like, does anybody know what some people, who's the actor who plays Iron Man? Robert Downey Jr. Does anybody know what some people call Robert Downey Jr.? RDJ. Does it say, oh, RDJ, RDJ's here. RDJ's in the house, right? Okay? So that's just a shorthand, right? It's the same person, it's the same thing. So KHP, that's the initials for potassium hydrogen phthalate. Now, what is the actual chemical formula for potassium hydrogen phthalate? KC7H4O2COOH. Okay? So all we're doing, I know I drew a picture of this yesterday, but this question is basically asking, you've got a volumetric flask. Do you remember using volumetric flasks? They've got a little line on them, and they say fill up to this line, that kind of thing, right? Okay, so it's saying we dissolve 3.07 grams. So I've got a little beaker, and it's got a pile of some solid or whatever. I'm going to put this into here, and then I'm going to fill up the volumetric flask until that mark. And you should be able to tell me what the concentration of this substance is, right? Now, so far, have I mentioned a chemical reaction? No. So far, has one thing reacted with another thing? No. So when you're looking for the concentration in moles per liter of KHP, right? Why do people call it KHP? Yeah, sorry. Why do people call it KHP? Yeah, well, people, they don't want to have to say potassium hydrogen phthalate a million times in a row. We just say KHP because it's just short and chemists are lazy, right? So how am I going to get the moles per liter of potassium hydrogen phthalate? If there's no molar ratio because there's no reaction, do you see moles anywhere in here?
Find the molar mass.
Yeah, exactly. We need to find the molar mass of this thing. Did anybody find the molar mass of potassium hydrogen phthalate? What was it, Idris? 204.23. So in 1 mole of potassium hydrogen phthalate, 204.23?
Yes.
23 grams of it. Perfect. So we want the concentration. Okay, we've got to get rid of grams. There are 3.07 grams of this stuff. And how much water did we put it into? 100 milliliters or 0.100 liters of the stuff. So when you do this, you go that divided by that times that divided by that.
0.15.
0.150 moles per liter. Why did I say 0.150? You need to carry over the significant digits, right? Yeah, that's the only reason. So I see 5, 3, 3, so I need 3 in my final answer. Good. Okay, awesome. Okay. Why did I ask you to do that? It's because that's a critical skill that's going to be needed for today. We're going to need that information for later on in class today. But I just want to go back over, I'm just going to go way back to that second slide. When we're doing a titration, what's the purpose of doing a titration? Yeah, so there's in essence, there's one reason why you want to do a titration. You want to find something out about either your sample or you want to find something out about your titrant. That's the only two things. So typically you want to either find the concentration of your titrant or you want to find the concentration of your sample. Now, in order to do that, you need 3 other things. If you want to find the concentration of your sample, you need the concentration of your titrant and both volumes. Think of it the exact same way that we would think of a solution stoichiometry problem. This is exactly the same as a solution stoichiometry problem. And so just to prove it to you, I put up a solution stoichiometry problem over on the whiteboard here. So do you have any room anywhere on that notes packet? I don't know if you do, I'm asking you. On the very back, right? I know this is a little bit disjointed, but just roll with me for a second. Okay. A student is titrating 20 milliliter samples. You do not have to write this down. This is totally fine. You do not have to write this down. What I would do is I would put this on the very back of your booklet. Again, you don't have to write down all of the stuff, but I would write down this chemical reaction on the very back of your booklet. That's what I would do. But let's just read it. A student is titrating 20 milliliter samples of hydrochloric acid with 0.500 mole per liter sodium hydroxide. If the average volume of the titrant used is 13.41 milliliters, we're asking ourselves, what is the concentration of hydrochloric acid? Again, you don't have to write down the question. You can if you want. That's totally fine. But I would write down the reaction for sure. So let's think about this. Oh yeah. You just want a pen? Let me take that. Okay. So we've got sodium hydroxide reacting with hydrochloric acid. Now, read the question. What I want to know, which chemical is in the Erlenmeyer flask and which chemical is in the Burette? Can you, is it possible for you to figure out which chemical is in which?
Yeah, the titrant.
The titrant is always in the Burette and the sample is always in the Erlenmeyer flask. So Wim, which one, just talk about one of these. Which one do you know is in which one of these?
I think the HCl is in
The Erlenmeyer flask. And then the sodium hydroxide is in the Burette. Yeah, you would be totally right. 100%. So hopefully you're happy with that, right? So it says 20 milliliter samples of HCl. So these are my samples of HCl. And then we've got 0.500 moles per liter of sodium hydroxide. So we can either add more or less of this, right, by opening up, what's the name of this thing again? Nobody wants to say it. It's either a valve or a stopcock, right? It's okay, you can say it, it's a thing, don't worry about it. Okay. So, what we want to do, we've got 20 milliliters in here, right? Do you know the concentration of hydrochloric acid in here? No, that's the whole point. We're trying to find the concentration of hydrochloric acid in here. In order to do that, you need to know the volume of this, you need to know the volume that leaves here, and remember it's an average of like 3 or 4 trials, right? You need to know the average volume that left the burette, but you also need to know the concentration of this. No problem. So let's go ahead and let's start solving this. This is a regular, everyday solution stoichiometry problem. This is going to be really, hopefully, straightforward. Do you know anything about the sodium hydroxide? Anything at all? Yeah, absolutely. Its concentration is 0.500 moles in 1 liter. 100% you know that. Do you know anything else about the sodium hydroxide? Yeah, you know the average volume that was used. What was the average volume that was used?
13.41.
You know that we used 13.41 milliliters of this stuff. Okay. What about the hydrochloric acid? Do you know anything about the hydrochloric acid?
Volume.
You know the volume, we used 20.00 milliliters of this stuff. And then what are we looking for? You're looking for the concentration of the hydrochloric acid. Now, typically, it's giving you information about one thing and asking about another thing, right? So what do you need? What in addition to all this stuff, what do you need?
Balance.
You need a balanced chemical reaction, right? Go ahead and balance this for me then. It's already balanced. Okay, cool. Yeah, it's totally balanced. Believe me when I say this is balanced, okay? So 1 sodium, 1 sodium, 1 oxygen, 2 hydrogens, 2 hydrogens, 1 chlorine, 1 chlorine. Good. Now, so because it's balanced, what can we get from the balanced chemical equation?
Molar ratio.
The molar ratio. And molar ratio is unknown over given. So 1 mole of HCl for every 1 mole of sodium hydroxide. So what this is saying is, on average, I needed to add 13.4 milliliters of that base for every 20 milliliters of the acid that I had. So, how difficult would it be to do this as a stoichiometry problem? Could we do this? Yeah? What are you going to start with? What do we want to start with? We want concentration in moles per liter of HCl. Do you see any moles of HCl anywhere?
Yes.
Yes. 1 mole of HCl for every 1 mole of sodium hydroxide. And then we're going to cancel out moles of sodium hydroxide. How? When? Concentration, good. 0.500 moles of sodium hydroxide for every 1 liter of sodium hydroxide. Did we use 1 liter of sodium hydroxide? No. We used, on average, 13.41 liters, or milliliters. 13.41 milliliters. Now, why am I not afraid of putting milli in here? Normally we would want liters, but why am I not afraid of putting mils? Yeah, there's a milli over here and there's a milli over here, so I'm fairly confident they will cancel each other out. The most common problem people have with this is accidentally swapping the two volumes, not putting the appropriate volume on top. That's why every time I write down a unit, I write down what substance that unit is affiliated with or associated with. So I would pretty please like you to try this out. Go ahead and tell me what the concentration of the hydrogen chloride is. Does anybody need a calculator? Cassidy, would you like a calculator? Can you catch? Good. I know it's nerve-wracking to have a calculator fly at your face, but I don't know, is this like 0.34? 335? Yeah. So we're going to get a concentration of 0.335 moles per liter of our hydrogen chloride. Now, if I were to give you this question, if I were to just give you this question, could you have done it at the beginning of class today? Would you have been relatively confident that you could do this? Well, that's a titration question. We're literally, that's all we're doing is just, that's a titration question. Why was yesterday so much harder? Wow, why was yesterday so much harder? That's a good question. First of all, what information did I give you in the original problem here? I gave you 2 volumes and a concentration. In the problem yesterday, you had to find the concentration. That was the only additional problem that you had to do. It was, and all you had to do, remember, let's go back. All you had to do was calculate the concentration of sodium carbonate, right? And then once you had that, once you had the concentration of sodium carbonate, then this was just a regular, right? Could you have done this if I just gave you the reaction, that, and that? Could you have found the concentration?
Yeah.
Yeah, I think you could have. That was all we did yesterday. Can you believe that? Do you believe me when I say that? No, you don't. But that was all we did yesterday. So it's really, I think, just the problem was we didn't start super simple. I was hoping that we could just catch on that, oh, we just got to find this concentration, and then it's just a solution stoichiometry problem. That's all we had to do, right? But this is all titrations are. It's solution stoichiometry. 2 volumes and a concentration, boom, find the other concentration. That's it, done. Now, it's a tiny little bit more complicated in that I also gave you the average volume of the titrant, right? Where here, you calculated the average volume of the titrant, right? But I mean, how difficult is calculating the average volume of the titrant? Nah, this is not a big deal. Okay, so that's all I wanted. That's all I wanted to say. So let's skip to page 4. Okay, we're going to talk about standardizing titrant solutions now. So let's see. I don't know how many times I'm going to say this today. Probably a lot, and I apologize straight out of the gate. I'm starting to learn more things as I teach. I learn more and more about myself, and I'm a very kind of a broken record sometimes. I'm a very repetitious person. Okay? So I've got a titrant and a sample. In order to do a titration, what 3 things do I need to know? Volume, and one of the concentrations. Does it matter which concentration I need? No. As long as you're given one of these concentrations. Okay? What?
Could you get to concentration with number volume?
Yes, you totally could. You could predict, right? If you knew this concentration, and you knew this volume, then you could like predict how much volume of this thing you would need. Totally, 100% you could do that. But because the purpose of a titration, I mean, is it pretty easy to get a volume out of this thing? It's you get an initial reading and a final reading, and you subtract the two things, and so it's easy to get volumes, but it's not easy to get concentration. But that's totally something you can do. Anyways, let's think about this. So let's say I've got a sample and I've got titrant, and I don't know either of these concentrations. Can I do a titration if I don't know either of these concentrations? No, you cannot do it. So what you have to do, let's say I've got sample number 1, and I want to know its concentration. In order to do that, I need to know the concentration of the titrant, but I don't. Son of a gun. What am I going to do?
Yes.
You can guess. You just throw caution to the wind and just pick a number. That's probably not a good idea, though. Okay? So can we all agree this combination isn't going to work right now? It's not going to work until we know the concentration of this titrant, right? Okay, so what could I do about that? Could I pick a new sample that I know the concentration of really, really accurately? And if I know this concentration, can I get this concentration?
Yes.
Yes. Now that I know this concentration, now can I get this concentration? Is that okay? That's complicated. Can we draw that out? Yeah, let's, and you know, you're better at drawing than I am, so this is going to be... Okay, so let's draw our scenario. We've got, what's this long glass tubing called with the stopcock on the end? A burette, okay? So we've got our burette. And this is how we draw a burette. Oh man, that's terrible. Whatever, okay? It's got some graduations. Idris, was that you making fun of me? Okay, so I've got sample number 1. I've got sample number 1. And in order to find this concentration, we need the concentration of our titrant. So we need the concentration of our titrant to find the concentration of sample number 1. But do we have that all the time? Do you know for sure? Do we always have the concentration of our titrant? No. And I'm going to tell you, I'm going to show you why that's not always possible to find or to know immediately the concentration of your titrant. So I'll know that for a second. Okay, so what we need is we need and it doesn't matter where you draw this is totally fine. We need a primary standard. Now the reason it's called a primary standard is because you don't need any other solutions to find the concentration of this. This is your primary source of information. That's why it's called a primary standard. So our primary standard, if we know what that means, is that's a known concentration. We're going to use this substance. We're going to use our primary standard. We're going to use this to find the concentration of the titrant. And then, once we know the concentration of the titrant, then we can find the concentration of the sample. Does that kind of make sense? So the problem stems from, if you don't know this concentration, there's no way you can know that concentration. The way you find that concentration is you do a titration first. Before you really start your experiment, you titrate something else. And the primary standard that's often used, hopefully this isn't very surprising, is a little something called potassium hydrogen phthalate. Potassium hydrogen phthalate is a compound that doesn't absorb water, okay? Now, I'm gonna talk to you about the problem with sometimes our titrant. What was our titrant? What chemical was our titrant in this example here?
That was a base.
Yeah, but not just any base. What base was it? What's the name of it?
Hydroxide.
Sodium hydroxide, right? Sodium hydroxide. Okay, here's the problem. Do you have like a little bit more room on the sheet of paper?
No, unfortunately, yes.
Ah. Okay, anywhere at all, it doesn't really matter, okay? Here's the problem. Sodium hydroxide no.
Now I just used all my room.
Hygroscopic. Hygroscopic means this compound, if you leave it out on the counter, it will absorb water from the environment. Okay? So this is not a term that you need to know. I will never test you on this term. That's why I put an asterisk. You don't need to know. Okay? This is not on the test. Yeah, whatever. That's fine. Okay? Okay, but here's the problem with it. If I have a container of it, so let's say I have a container and it's got a cap on it and everything. Do you know what I'm drawing? I'm drawing a bottle with a cap and everything. Does that kind of look like a bottle with a cap?
It looks exactly.
Yeah, okay, all right, okay. That's pretty good for me. All right. So we've got a bunch of sodium hydroxide. This is not a liquid. Sodium hydroxide isn't a liquid. It's a solid at room temperature, okay? So let's say the initial mass of my sodium hydroxide in this bottle, I don't know, let's say there's 45.0 grams of it in this bottle, okay? The moment I open up the bottle, what do I introduce into the bottle? Oxygen from the environment, water vapor from the environment. So what's going to happen to the mass of sodium hydroxide? If I left the cap off of this thing, or if I just take the cap off and then put it back on, what's going to happen to the mass of this solid over time? The final mass, it's absorbing water, right? So the final mass is going to be like 46.2 grams or something like that. Well, okay, you're probably thinking to yourself, nobody cares. Walton, straight up, nobody in this room cares. And I would kind of agree with you. Stop making fun of me, it's okay. All right? So I would agree with you. For the most part, that doesn't seem like that big of a deal. But when you go to make your titrant, what are you going to make your sodium hydroxide, your aqueous sodium hydroxide from? You're going to make it from dry sodium hydroxide, right? If you want to make a concentration, a very specific concentration, that means you need to weigh out a very specific mass of sodium hydroxide. Tell me, if I take 5 grams out of this bottle, is it really 5 grams of sodium hydroxide? No, it's like 4.9 grams of sodium hydroxide and a little bit of water. That's a problem. That means you know kind of what your concentration of sodium hydroxide is, but you don't really know what your concentration of sodium hydroxide is. KHP is not hygroscopic. It doesn't react with anything in the environment unless you perform some sort of an aqueous reaction. So KHP, what I'm trying to get at is KHP doesn't change. It doesn't react until you put it in water and force it to react with something. So if I have a bottle of potassium hydrogen phthalate, if I have 50 grams of it and I leave it open for the next 30 years, I'm still going to have 50 grams of it. The mass isn't going to change. So it's what we call a primary standard. We can make a primary standard solution from it, and then we can do 2 different reactions. Are we kind of with it so far? A little bit? So that's what you have to do. You're going to have to do this in the lab next Monday, Tuesday, Wednesday. I told you were going into the lab today. We're not going to do the same thing. We're still going to go into the lab, but we're not going to do the same thing that I was kind of hoping we could do, just because I knew that it was going to take a while to talk about this lab and talk about what we want to do. Okay? But we're still going to go into the lab, and we're going to look at some burettes, and we're going to try and read some volumes, and we're going to come back in here, and I'm going to yell at you because you were wrong, and that's fine. That's okay. It'll be fine.
That's not okay.
Yeah, no, it's okay. I'm not going to yell. Okay, to make a primary standard, we just need to dissolve a precise mass of solute in a precise volume of water. Was that okay? That was fairly straightforward? So now we can use our primary standard, right? I'm going to draw this again. We're going to use our primary standard. And from there, we can get the concentration of our titrant. And then from the concentration of our titrant, then we can finally analyze our proper sample. That's terrible, but that's fine, whatever. So you need to do you're going to have to do 2 titrations. On Tuesday, you're going to do the first one, and on Wednesday, you're going to do the second titration. And it'll be fine, don't worry about it. It'll be good. So let's take a look. Let's take a look at what we're going to do on the first titration day. So here we go. We've got a reaction. You are titrating 10 milliliter samples of that KHP. Why is KHP important? Yeah, we know the concentration of KHP to the T. We know exactly what concentration we've made because you measured the mass, you measured the volume of water, and you made the solution. Okay? So you're gonna pull out from your volumetric flask. You're gonna pipette out 10 milliliter samples, and we're going to do this reaction. Remember, I'm using the shorthand, right? But what's important for you to understand is the K and the P, the potassium and the phthalate, don't react. Sodium hydroxide's a base. What does it like to react with? Water. Yeah, okay. But it likes to react with acids, and acids contain hydrogens. So that's all I want to bring your attention to right now. The base is going to steal what from the acid? The hydrogen. Okay? So the sodium and the hydrogen swap places. So instead of KHP, what are we going to get? KNAP. Is that okay? That's all. So this has stolen the hydrogen away, and it turned into water. Boom, that's all that happened in this reaction. That's it. Okay? Now, you attempt 4 trials, and the results are here below. So let's take a look at this. The titration of 10 milliliter samples of 0.150 moles per liter potassium hydrogen phthalate with sodium hydroxide. How much volume, what volume of titrant did we use in the first trial? Take the final minus the initial, and what are you going to get? Yeah, it's 10.9 minus 0.10. There's an extra 0 there. I don't know why it's there. Go ahead. Do this math. Go the final minus the initial, and then tell me whether or not you want to use all 4 trials. Okay. Why do you want to get rid of the first one? So this one's 10.2, this one's 10.3, and this one's 10.2, right? Yep. So which one of these is not within our 0.2 milliliter range? The first one. So that. And how could you have how could you tell without even doing the math? Wim. So yeah, this endpoint was dark pink. We wanted light pink, like the palest pink you could possibly pale pink imagine, okay? So what's the average volume here? 10.23 repeating. Good. Milliliters. Okay. All of a sudden, this is solution stoichiometry at its best. That's all we're doing. We're doing solution stoichiometry. What is your reaction? Do you have a reaction here already? Yeah, you have a reaction for sure. So do you wanna rewrite this reaction and put the stuff down below, or do you think there's enough room for you to summarize all our information below the reaction the way it is?
I don't know. No, let's rewrite it.
Okay, I'm gonna rewrite it. That's fine. Whatever. It's okay. So KHP aqueous. Remember, it's not actually phosphorus that's in here. That stands for phthalate. Plus sodium hydroxide, KNAP, or NAP. Gives us H2O. Good, here's our reaction. No problem. Do you know anything? Read the question for me. I'm not going to tell you. But I want you should be able to put a bunch of pieces of information below KHP and a bunch of like 2 pieces of information below KHP and 2 pieces of information below NaOH. Go ahead, right? We know 2 volumes and we know 1 concentration, so put them under the reaction. Summarize the information. 10.2 plus 10.3 plus 10.2. 10.3 equals you're not using brackets. Okay? So if you go 10.2 plus 10.3 plus 10.2 divided by 3, what's the only thing in here you're dividing by 3? Just that last number. That's the last number. That's the only thing you're dividing by 3. So you gotta wear it down, right? Yeah, but you could put brackets. You gotta do everything. 10.2 plus 10.3 plus 10.2 bracket. Now we're gonna divide whatever we get there by 3. Does that make sense? But you can do them separately, whatever. Okay. So the concentration of potassium hydrogen phthalate was 0.150 moles per 1 liter. How much, what volume of KHP did we use? 10 milliliters, right? 10 milliliters, 0.0. Okay, and do we know anything about the sodium hydroxide? Do we know anything about the sodium hydroxide? What are you looking for? You're looking for the concentration of sodium hydroxide, and what do you know? The only thing you know about it, Wim? Right? That's the average amount of sodium hydroxide that was added to these trials. On average, that's how much was added. Okay, now what's the molar ratio between these two things? It's 1 to 1, right? So 1 mole of sodium hydroxide for every 1 mole of KHP. Good. So what I want you to do, go right ahead. You go right ahead and you look for the concentration of sodium hydroxide. And if you finish this, you can just flip the page over and you can start doing the next one. Okay. Again, I want to bring your attention to where the volumes go, right? How did I know to put the volume of KHP on top? Because there was KHP down here, and there's another reason why I knew not to put sodium hydroxide on top. It's because we're looking for the volume, right? Moles per liter. The liters of sodium hydroxide need to go on the bottom, right? Yeah, cheers up.
I'm confused, and maybe I missed this before, but how can you have the 1 liter over there and then 10 milliliters on the top? Why would you convert milliliters into liters?
I could. You totally could, right? So this would be 0.01 liters, and this would be 0.01023 liters, right? But the reason why is because milli and milli cancel out, and then it becomes like you had liters and liters anyways. So it's fine. Yeah, the milli here and the milli here. You can do it either way. The math will work out whether or not you convert both of them to liters or you keep both of them in milliliters. You got to do both. You got to do the same thing for both. If you change one to liters, you got to change both to liters.
Okay.
Yeah.
Thank you.
Okay, yes or no, you got 0.147 moles per liter. Good, okay, awesome. Okay, so what did we do? I wanna keep you, I wanna bring you back to this. We used a primary standard to get a concentration of our titrant. Our titrant, in this case, was sodium hydroxide, right? So, our concentration of sodium hydroxide is 0.147 moles per liter. Now, we can actually titrate our real sample. Now we can titrate our real, like, honest to goodness sample, now that we know this concentration of the titrant. So, you're titrating 10 milliliter samples of a solution of vinegar, right? You attempt 4 trials and the results are below. The sodium hydroxide, what did we just find out its concentration was? You just found that out. So now what you can do is you can do a titration of vinegar and figure out what the concentration of vinegar is. Okay? Or vinegar is just, sorry, I don't know if I've ever said this before, but vinegar is just, it's just acetic acid. That's all it is. A solution of vinegar is just straight up acetic acid. That's what you buy from the grocery store every single time. 5% solution every single time. Yeah?
Since you're carrying over the concentration of sodium hydroxide, should you not have done significantly?
Technically, because we're not really done the problem yet, we probably should not have carried over our significant digits, right? But it's almost like you can treat this as 2 separate problems. First, you're trying to find the concentration of sodium hydroxide. Then you're trying to find the concentration of acetic acid. So I agree with you. That's a really good point, Stephanie. Never round till the end, right? Yeah. But for the purposes of this, we're gonna assume this is properly 0.147. Okay. Well, let's look at this. Our titration of 10 milliliters of vinegar, right? Our titration of 10 milliliters of vinegar, okay? So do you know how much titrant you used in each sample, or for each trial? Let's go ahead and calculate that. Go ahead, figure out what volume you used every single time. And I want to point out something, okay? This, you might, I don't know, you might not have ever thought about this before, but we've got our burette, and our liquid starts way up here, right? And as we open up the stopcock and as we let our titrant out, what happens to the level of this liquid? It's going to drop, right? So it's going to drop, and we're going to read it once we're done. Okay, now, so this is our first trial. We started here and we finished here. So our final volume is this, whatever this is. Our final volume is 14.2 milliliters. Do you have to add more the next time you do a titration? Or can you just keep going from where you left off? You just keep going. So your final volume from the first trial becomes the initial volume from the second trial. Does that make sense? The level of the water didn't change, right? So hopefully you recognize the final volume from this trial becomes the initial volume for the next trial. The final volume from here becomes the initial here. Why does the final volume here not become the initial here? I'm curious. Do you think at some point in time our level's going to get too low so that if we did try this for a fourth time in a row, we might run out? And if you run out, you die. No. If you run out, you just got to start all the way over. So you might as well just fill it all the way back up and then start going again. Does that make sense? But your final becomes your initial. Anyways, figure out which volumes you want to use and figure out what the average volume is, please. Hmm? 11.9 thick. I did the average between 12, 11.9, and 12. It's an acid and base. The base steals the hydrogen. Well, we'll go through it together. We will go through it together. It's fine. Okay, you got 14.1, and then what'd you get here? 12.0, what'd you get here? 11.9, what'd you get here? 12.0. That means your average, when I do this in my head, I get an average volume of 11.966666666, right? Okay, good. Okay. So the average volume, 11.96 repeating. That's fine. I should say milliliters, sorry. Okay, which trial are we not going to use? Okay, it just happens to be the first one. It happens to be the first one so far, and I'll tell you why that is on Monday. We'll talk about why that is. What is the concentration of vinegar? Well, first of all, we need a reaction. We're taking sodium hydroxide, and we're reacting it with vinegar. I'm curious, what do bases like to do? They like to steal hydrogens, right? So the hydroxide is going to steal the hydrogen. What does that mean we're going to get? What's our first product? Does that make sense? What are you going to get that's left over? The sodium. And then all of this junk, right? Yeah. What's this called? It's acetic acid, but without an H. What's CH3COO minus? Sodium acetate. Acetate. Yeah, acetic acid, acetate, right? Okay, perfect. Do you know any information about this stuff? Do you know any information at all? Sodium hydroxide. Do you know what volume of sodium hydroxide we used? Uh-oh. There's two different volumes, right? And we don't want to pick the wrong one, because if we pick the wrong one, we're going to screw up. Read the question.
10.00 for the
10. Wait, no.
Why? How did I get that information? Yeah, I got it from the average. But how did I know? How did I know the 11.6 belonged to the sodium hydroxide? Because it's saying titration of 10 milliliters of vinegar. The 10 milliliters goes with the vinegar. Which one of these is vinegar? The acetic acid, right? So this is 10 milliliters. And this is remember, this is the average volume of our titrant, and our titrant is sodium hydroxide in this case. All right, no problem. What else do you know? Do you know anything else about any of these two things?
That we need to calculate the concentration.
Okay, you're trying to find the concentration of vinegar. And you know the other one. Why do we know the other one?
We found it.
You just found it. Remember, that was the whole point, right? That was the whole point, was to try and find the concentration of our titrant so that we could use it in the second problem, right? Could you do this? Is this a solution stoichiometry problem you could answer, you could calculate? Let's find out.
Is it balanced?
I don't know, is it? Oh.
Yeah, it looks like it.
There is.
Oh, yeah.
Did I put the answer at the bottom of this quick page?
Yeah, you did. Wait, no.
On the other pages I did, but I didn't on here. Okay, let's see. We're going to get an extra 20% above that. So 0.1756. And when you round it, it's 0.176. Okay. 0.176 moles per liter. Cool? Cool. Okay. Now I feel like that's enough. I feel like that's enough, blah, 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 blah. I feel like that's enough kind of titration stuff for today. What I want to bring your attention to is reading a burette is no small task. I'm going to show you what a burette looks like. And I want to make sure you understand. That's terrible. Okay. This is what a burette looks like. I don't know how well you can see that. Right? That's what a burette looks like. And just like a pipette, anytime you have water inside something glass, what? It does that thing. The meniscus, right? Can you see the meniscus here? Yes, you can. Hopefully you can. Okay? Now, what I want to bring your attention to is that I've got something called a Meniscus Finder. It's a really simple piece of technology. It's white paper with a black line on it. Now, I don't know if you can tell, but when I use this, you can see the bottom of the meniscus quite clearly when you put it behind there. Now, what I want to know is the meniscus. I see a line here. There's a white line that starts right here. And I don't know why I can't write on it, but that's fine. There's a white line that is right here. And what I want to know is the meniscus below that line? Or is it above that line? Or is it exactly on that line? You can see that it's below that line, right? Now, when I put this behind it, yes or no, can you see that it's below the line? Okay, perfect. Now, what you wanna do when you're reading the meniscus of something is you want to try and identify, like our whole goal is we want to figure out what the volume of this is, and it's actually really phenomenally hard. Okay, it's really quite hard to do this unless you kind of have a different perspective. Let's see. I'm going to turn this here. Okay, that's a lot better. Okay, do you see the number 39? Yeah, the 39 is right where my black meniscus finder is. That's the 39. So what's above 39 here?
38.
38.
Yeah.
The numbers are going down. They're going up as you go down, if that makes sense. Okay? The numbers are increasing as you go down. Okay? So the volume is a really low number at the top and a really high number at the bottom. And that the only reason why is you always go final minus initial, and that always gives you a positive volume. That's the reason why it is. Okay, whatever. Okay, so let's think about this. Up here is 38. Down here is 39. So what's that line that it's really close to? 38.5. Now, I'm curious. Is this exactly on the line of 38.5?
Yeah.
I'm going to draw this a little bit again. Okay, so we've got our burette, and this is 38. This is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This is 39. Okay, so our meniscus, it looks like, is right here, where it's just barely below the line. So I'm curious, is it exactly 38.5? No, but you know it's greater than 38.5, right? 38.5. Now you have to guess this next digit.
9, 4, 8.
No, shut up. Okay, this is 38.5. What's the next graduation? 38.6. Okay, is it closer to 0.5 or closer to 0.6? Closer to 0.5. Is it exactly halfway between? No, so it's not 38.55. It's less than 5.5. 5.2? 5.1? 5.3? Which one is it? Can you be sure? Are you guessing? Yes, you're guessing. The answer is objectively yes, you're guessing. Okay? So yes, you're guessing, but it's okay. Do you remember us saying significant digits express your certainty of a number? 38.52. The last number you record should have some uncertainty. If there wasn't uncertainty, that means you can be more precise than that. Whenever you're reading a burette, you should always have 2 decimal places. We know for sure this is in between 38.5 and 38.6, so it's 38.52. If somebody else guessed 38.53, would that be okay? Yes, that's a perfectly valid guess. Okay? So what I want you to do, I know there's only like 8 minutes left, okay? There's only 8 minutes, but there's 7 burettes on the Chem 2 lab bench. I want you and your friends, okay, Idris, I want you by yourself and everybody else as friends, okay? I want you to take, if you want meniscus finders, you go ahead and use them, but you don't have to, okay? I want you to pick one burette and you and your friends try and agree on a value or get really close to a value. Then when you come back in, I'm going to show you what I got for
Yes.
It's going to be hard for people to look from different